be able to do this the homework for. And as always, I encourage you to start early and try often. Has anyone taken a stab at homework 4 yet? And if so, any questions? Yes.
Yeah, are you ever going to show us like like an algorithm to do SVM on actual record?
In about the next 10 minutes.
Oh, okay.
Yes.
The data you give doesn't. So, in previous homeworks, we wrap the bias in with our feature set, right? So in the data in the Astro set, that
Yes.
bias isn't wrapped in.
Yes, you have to add an extra feature. That's an excellent observation, actually. And in fact, that's a good point. So the data does not have the bias a feature that's bias, and you have to add the bias feature. The best way to do it, my recommendation would be always add a bias feature, whether you believe the data has it or not. Because if the data has it, sure, you get two features that are always on, and the bias weights will be shared across the both of them. Does not matter. If it does not have it, then you get the added benefit. That's the first observation. The second thing is, this is the liblinear format. And the liblinear format is a fairly common format that has been popularized by the fact that the people who wrote the software liblinear have done a fantastic job, and it's become like one of the standard libraries that people use. And this was the data set format that they invented. And if you look at the data in the liblinear format, according to the definition of the format, feature 0 should never be used. And the reason for that is they allocate feature 0 for a bias feature internally. Yes.
In the homework, you asked us to calculate the distance from the origin for some of the data. By adding that bias term, do you want us to shift the origin up? So
Which
I believe it's in number 2, but I don't have it directly on there.
no, is this the experiment section?
Yeah.
Yes.
Calculate the distance of.
The furthest point.
Oh, I see. Yeah, that's not going to make. Either way, make an assumption, make it very clear, and there are really only two answers. Either you add a bias feature and calculate the distance, or you don't. So your answers should be self-consistent. Other questions?
Just one more. Also, when we're mapping features to the new dimensionality, do we also include? We count the bias as one of those features?
Yes.
Okay.
Because if you do, actually that's a interesting thought. In fact, what I would recommend is take a tiny example with maybe 2 features and add a bias feature, and manually map it to maybe a quadratic space, with and without. See what happens. In one of them will be way more expressive than the other. And you want that, or you want to try that out. In fact, we'll be talking a lot about expressivity of these kinds of mappings today. Other questions? So one of the things about this homework is that we've given you a data set which we didn't construct it. It exists out there, and there is no 100% perfect classifier for that. You may have to make some choices in making this work. Things like, should you add a bias feature or should you not? These are the kinds of choices that you have to make anyway when you actually apply these algorithms on real data. So, if you notice, the general trend has been the first homework we gave you a data set that we controlled completely. We knew exactly what was going on, and as the semester is progressing, we are giving you more and more noisy or more real-world data sets with fewer instructions on what to do. The idea being that you play around with the data and kind of make assumptions, and just tell us what you assume, and you'll be graded on not on the assumptions that you make, but on how you manage to make them work. But in real life, when you apply any of these algorithms on, say, building a classifier that, say, classifies birds, who knows what the feature space is? Who knows what kinds of assumptions you need to make, and those are the kinds of decisions that you have to anyway be comfortable making. And that's really part of the modeling problem. Yes.
I'm sorry, I realized you answered that question way back at the beginning.
Okay. Right. Other questions? So we were, at the end of the last lecture, we were towards the end, almost came to the end of how to optimize the SVM objective. Just to remind you, we are in the middle of the SVM lecture, and the objective is to find a weight vector that maximizes the margin and also tries to, in some sense, discard as many examples as possible as needed to maximize the margin. And make this decision jointly by writing down an optimization problem with two terms. It's right at the top of the slide. The first term is saying minimize, and we need to minimize this function with respect to W. W is a vector. We need to minimize this function, and the first term in this function says minimize the norm of W. I like weight vectors that have a low norm. And the reason for that is if the weight vector has a low norm, through what might seem, through a series of rather subtle arguments, it turns out, we can guarantee that it will have a larger VC dimension and hence better generalization. So the first term maximizes the margin and pushes towards generalization. The second term in the summation is called the hinge loss. It's the hinge loss over the entire data set. It is saying what should this weight vector be penalized for a decision on an example. If it makes a mistake, it should get a linear penalty. If it makes no mistakes and places that particular point outside the margin, it should pay no penalty, and that's the max of 0, 1 minus YW transpose X. So the max will be 0. And the interesting part is if it does not make a mistake, namely y, the sign of y and W transpose X are the same, and yet W transpose X is less than within the margin, it should still pay a penalty because we don't like weight vectors that puts points inside the margin. And in the last lecture we saw how this formulation is just an instance of a larger class of problems which are called empirical risk minimization or regularized risk minimization. The first term is called a regularizer. The regularizer is a function that pushes for generalization, that restricts the capacity of classifiers and hence allows it to get better pack guarantees. The second term is called the empirical loss, which prefers classifiers which make fewer training errors. And so we want to trade off between making fewer training errors and better generalization. So that we saw all of this in the last lecture, and we started looking at how to solve this problem. And one answer is, really, this is a quadratic program. A quadratic program is simply an optimization problem in which the variables that need to be optimized are in a quadratic form. So you have a W transpose W, which is really W squared, or sigma Wi squared. The sum over, it's the dot product, it's the norm of a vector, which is quadratic, so this is a quadratic program. And there are standard methods out there, so we can just appeal to one of those. But because we know that this method, this objective has certain special, has a rather special form instead, which means it's a giant summation over the entire training set, we can do a little better. So we can use gradient descent, or even better, we can do something called stochastic gradient descent. And stochastic gradient descent is the following recipe. It's right here. You initialize your parameters. Because this is a convex problem, it does not matter where we initialize. So let's just say we initialize it to 0. In general, we could initialize it to a random vector. And then training proceeds in multiple epochs. At each step, what you do is you pick a random example. In practice, actually, what we do is not one example, but we pick a small subset called the mini batch, but it doesn't matter. For now, for simplicity, let's just say we pick a random one example. and pretend that this one example is our entire training set. And so we are going to try to estimate the gradient of our data over the entire training set, that big summation, by pretending that this is a sample from the set of possible gradients. So we pretend that this is the entire training set and take the derivative of the function where the summation is over just one element. Now that reduces the computational load of this summation, and then we take a gradient step. So this is gradient descent. So you find a gradient is the direction in which the function increases most sharply. So you go in the opposite direction because we like smaller values. And that's pretty much it. And roughly this is where we left off at the end of the last lecture. Questions about any of this? Yes?
You mentioned VC dimension. I can't remember how that, I mean, I remember the expression we're trying to minimize and stuff, but how is it that this minimizes the VC dimension? Or I can't remember that.
Right, so it's a, like I said, it's a fairly subtle argument, and let me move to a slide that has more space. The VC dimension of a linear classifier is VC dimension is either d plus 1 or r square over gamma square plus 1. Whichever one of these is
Oh, yeah, now I remember that.
right. So maximizing gamma gives us a lower VC dimension because gamma gets small, this gets big. And then maximizing gamma is equivalent to minimizing the norm of the weight factor. This is, like I said, this argument is slightly subtle. There are more details here than I presented in the slides. So what I encourage is to go to the right to the beginning of this entire SVM lecture and try to work back this reasoning. Work the reasoning out as to why maximizing gamma is the same as minimizing the norm of W, and why minimizing the norm of W gives better generalization. This really ties together a lot of this SVM lecture and a tiny bit of the agnostic learning for real valued hypothesis spaces. Other questions? So what we're doing here is gradient descent. So the only thing that's left is to define what's the gradient of this function, of the hinge function, max of W, 1, 0 and 1 minus W transpose X. And as someone pointed out in the last lecture, this function is not differentiable. So we really can't go down a gradient of a function that's not differentiable. So we need to introduce a new concept. So just to point out, given if I have chosen a single example xi yi, we are now writing down an objective function pretending that this was the entire training set, and that's this function. I'm going to call that jt of w at the tth time step. It is the regularizer plus some c is this trade-off term, times the hinge loss. Everything here is fine except for the hinge loss because the hinge is not differentiable. If you want pictures, it looks like this. As a function of y w transpose x, remember the hinge was, this is say 0, this is 1, it is 0 all the way to here, and then it goes up. So at this point, it's not differentiable. So we need a generalization of the idea of a gradient of basically derivatives that lets us solve this optimization problem. And this is a very neat trick, and it's something that has now become basically it shows up everywhere, and it's baked into a lot of code libraries out there. And the idea is something, it's a generalization of the idea of gradients. It's called a subgradient. And there are many ways of introducing subgradients. One way of thinking about it is, first of all, let's think of what is a gradient. Gradient is simply of a function. The gradient of a function is the derivative of that function. If you have the function f of x as x squared, then its gradient is 2x at any point. That's one way of thinking about it. That's just the algebra. from the geometric perspective, the gradient is actually the slope of the tangent. So basically there's a one-to-one mapping between tangents and the gradient of a function. What is a tangent? A tangent for a convex function is at any point, just remember the first time you ever encountered these tangents and such things. At any point for a function, the tangent is a line that touches the function at just that point and nowhere else. And for convex functions, the tangent is a line that touches the function at that point and is below the function everywhere else. The second part is important, below the function. So it's just a line. Now, a subtangent is a generalization of this idea of a tangent. It's any line that touches the function at that point. Remember, now we've gone from lines to hyperspaces, hyperplanes. We're going to n dimensions. A subtangent is any hyperplane that just touches the function at that point and lies below the function everywhere else. And the subgradient is simply the slope of that line. In fact, all those lines. That's the geometric idea. Questions?
So we must touch the function.
Yes. There is, of course, I mean, what I just described is kind of hand-wavy and no math definition. There's a formal definition. Question?
This may be a little off topic, but we're doing stochastic gradient descent because there is local minimas.
No, there's a global minimum.
Right. What do you do if there's local minimas how do you avoid local minimas and go for the global minima?
So remember that our function is convex. A convex function. Huh?
Because there's only one.
There's only every local minimum is also a global minimum because there's only one. But that works for this function, which is convenient. Very often, many interesting machine learning problems come with objective functions that are not convex. And so far, the prevailing wisdom has been, so what? It's a function, it has a gradient, you can go down. And let's see what happens. There is not much, there's some theory, but not much. Convex optimization is well understood. Non-convex optimization is a little less well understood, let's say.
Thank you.
So there is a formal definition of a subgradient, and I'm not going to talk about the math. You can check it out yourself. And in fact, Stephen Boyd has fantastic lectures on this. In fact, he's written a good survey as well. In fact, this picture is from Stephen Boyd. I'm going to go through this picture a bit. So the subgradient is the slope of all subtangents, or not a single one, but many. Let's consider this function here, f, and this function, it turns out, is differentiable everywhere except at this point x2. At all other points, there's only one subtangent, which is the tangent. There's only one line. In fact, this function is also convex. At all other points except x2, there's only one line that touches the function and lies below it, and that's the tangent. So the subgradient at every point except x2 is a set containing one element, which is the gradient. At x2, on the other hand, something interesting happens. We can draw not one but many, an infinite number of lines that satisfy that property. Here, this picture has two, but I could draw more. I could draw another line this way. So I could draw many, many lines that satisfy that property, and the subgradient at that point x2 is the slope of all those lines, or hyperplanes. Okay? Question?
It would be, because there isn't a unique slope, so would it be a set of?
It will be a set. It's an infinite set.
Okay.
There's not, at that point, there's no unique slope.
The second line you draw,
Yes.
is not a any.
Yes, I know. The second line I drew is a mess. So let's erase it and pretend it never existed. Well, this is not even a line. So, yes. Other questions? Something that doesn't have to do with my drawing skills? Yes.
So if all of those lines between those two at x2 are valid subgradients, which one do you choose?
Anyone. So that's the thing. Stochastic subgradient descent for a convex function is the following. If you have a convex function with a finite number of such discontinuous points of that are non-differentiable, you pick any subgradient and go down, you're guaranteed to get to the minimum. So that's what the theory of optimization tells us with respect to this setting, which is convenient because we have a function that has a finite number of non-differentiable points, the Hinge laws. So just a reminder, the function we have is half of W transpose W plus max C max 1 minus blah blah blah. And max is a piece of the story that's giving us trouble. And especially for max, there's a kind of a cool recipe for generating a subgradient. Not necessarily all, we just need one, right? So there's a cool recipe for generating a subgradient at any point W. The way to do it is first solve the max at that point. So for a particular W, here, notice that whether this is just a function of W. X and Y are fixed. It's the training example that we randomly chose. So this is just a function of W. For any particular W, this is this function is just a number, right? Given a W, this will compute a number. So the way to one way of generating subgradients is first solve the max for that particular W. If max of W transpose X is less than 1, then 1 minus that will be greater than 0. So that term will contribute to the gradient. That's this term here. If the max is 0, then this whole thing disappears. This block just disappears, and we just are left with a square. So we are roughly asking what's the derivative of W square, half W square with respect to W, and that's just W. So that's the first case. And in the second case, we are asking what's the, so once we solve the max, this function becomes, this is equal to half, or J of W is it's one of these two things, right? The function by definition, I've just expanded the definition of max here, and if this is true, if this condition holds. If max is 0, then it's just W transpose W, otherwise it is. So it has to be one of these two things, and at 0, it doesn't matter. Either both of them are the same. When the max, when Y W transpose X is equal to 0, then this whole thing becomes 0, the right hand term, second term. So it's continuous but not differentiable, so you just expand this into into this kind of a case by case analysis and just compute the derivative for each case. That's all there is, in fact. And this gives you a subgradient of that. Questions?
So is this an approximation or?
No, it's exact.
No, I mean using the subgradient is still the convergence.
Yes, it has the convergence guarantees. Did I see half a hand go up somewhere here? Okay. Okay, so what we have here is we've put together, so right now we have all the pieces of the puzzle that we need. I mean all the pieces that we need to solve the puzzle. So let's write this all into a single algorithm. So what we have, we started off, just to tell you this, remind you of the story of the algorithm, we started off by saying that we are going to do gradient descent. And then we pointed out, we observed that gradient descent is really a computationally painful strategy because you have to compute the gradient. To compute the gradient, you need to take a giant summation over the entire training set. So let's get quicker updates. So we went from gradient descent to stochastic gradient descent. Then we observed that really, gradient is not defined because this function is not differentiable. In fact, gradient or stochastic, either case, the gradient is not defined, so we need subgradients. So we went from gradient descent to stochastic gradient descent to stochastic subgradient descent, and that gives us our algorithm. This is not the entire algorithm. So the setting is we are given a training set. As always, I'm using xi and yi for examples and labels. X is a vector, y is either -1 or +1. You initialize your weight vector to something, it doesn't matter what, let's just say 0, and after learning, it's this weight vector that we'll return. Learning proceeds in multiple epochs, and at each epoch, what you do is, I've changed the algorithm slightly here. At each epoch, you iterate over the entire training set. So you have two loops here. So at each epoch, you iterate over the entire training set, and given a particular training example, you update the W to be W minus some learning rate times the gradient at that point. And the gradient at that point is that expression on top, so we can plug everything in and get an update loop. So if for this particular example xy, if yw transpose x is less than 1, in fact, let's consider the other case. If yw transpose x is greater than or equal to 1, the update rule says w is w minus the corresponding side of the gradient, the corresponding term in the gradient. In this case, it's just w equals w minus gamma w, which is this part here. You just shrink the w. Gamma is a number between 0 and 1, so this 1 minus gamma is a number between 0 and 1. So what this means, if yw transpose x is greater than 1, this particular point has already been placed on the correct side of the margin. The classifier is good enough at this point. So let's see if we can make w a little smaller. Let's see if we can maintain this correct prediction on the right side of the margin and get a few VC dimension points by making w transpose w small. How do you make w transpose w small? You just scale w by a small positive number. If you reduce that, w transpose w becomes smaller. So what you say, does that make sense? The else condition. We care about minimizing the norm of w, and this shrinking the norm of this update serves that purpose. Just the else part. So now let's look at the if part. If yw transpose x is less than 1. Less than 1 means one of two things. It can either be less than 0, in which case your classifier currently is making a mistake, or it can be greater than 0 and less than 1, in which case the classifier is okay, but it has put this point inside a margin. So let's try to move this point outside the margin. The way we do that is this part of the gradient kicks in. W times, basically the W becomes, the update becomes W is W minus gamma t times and that's exactly what, just when you clean this up, you get something like this. And now the update has two pieces to it. The first term, the first element here, still shrinks the W. What it's doing is gaining those VC dimension points, trying to maximize the margin. The second term increases the value of W by some scaled version of yi xi. Remember from perceptron long back, when we make a mistake, we added yx to the weight, and what that happened was this would slightly increase or decrease, move the score of that example in the right direction. So this basically completes the whole, almost completes the stochastic gradient descent for SVM. Questions about this? Yes.
Where is gamma coming from?
Where is gamma coming from? Good question. Gamma is the learning rate. Gamma is a learning rate, and it used to be considered to be like this kind of a magic thing that somehow you just know what's a good gamma. Over the last maybe decade, this question has been kind of, as a community, been resolved with some reasonably good estimates. I'll show you in a minute one version of gamma that seems to work in most cases.
Why do we scale W by 1 minus gamma and the other by gamma itself?
Because look at the update. So let's consider this case. This is W. Right? But the gradient is right? I just copied and I just took this part. And that's really W times 1 minus gamma plus gamma C.
Why do you have for epoch equal 1 to 2?
When you say why do you have it, what do you mean?
I mean, we just need stochastic trading example 1 at a time.
Yes, you need to find. So the theory of stochastic gradient descent says you don't need this approach. What you need to do is you have an infinite loop. You have this bucket of training examples, pick a random one, take a gradient step, put it back, or it doesn't matter. You have another, pick another example, put it and take a gradient step. Keep doing that forever.
For all the trading.
No, forever. At the convergence is in expectation this will converge to the optimum. In order to simulate this idea of forever, you stop at t.
Could you do a different stopping criteria, such as the distance from your last?
Yes, in fact, that is also frequently done. Yeah, that's also frequently done. So you keep track of the objective value at after each epoch, let's say. Remember that stochastic gradient descent is not guaranteed to reduce the value of the objective at each step, because this is stochastic. So you can't expect a decrease after every inner loop update. So you can track the value of the objective after every epoch.
Or could you potentially, after say like every 10 epochs, you do a batch gradient, one step of batch gradient descent, and stop if that update is small?
Yeah, you could do that. I mean, there are tricks. The problem with batch gradient descent is it's actually quite slow.
Well, I'd just say like one.
Yeah,
just to see if you're at.
Yeah, you can. There are multiple ways of deciding stopping criteria. By far, the most common one is just to pick a t. So, for example, by the way, this is roughly, a variant of this is roughly the most common algorithm that's used in machine learning. Not just for SVM, but for most empirical loss minimization. You might have heard, those of you who might have seen neural networks before might have heard of the backpropagation algorithm. It turns out backpropagation is actually stochastic gradient descent with some memoization thrown in, so that with more computational tricks thrown in. And the most common way of deciding stopping criteria, there are two ways. One, you run it for 10 iterations and hope it works. Or two, do something like what you said. Keep track of some quantity like the objective along the way, and if the changes are too small, then stop update. Typically the former, meaning picking a t, is easier, of course, in terms of writing code. The latter does not seem to give the benefit it seems to promise. So that's why the most common one is just pick a number of epochs. So one little bit of one other change here, which is actually crucial. I mean, it's one of those things that if you don't do it, makes or breaks the quality of the classifier, is before you get into an epoch, before you start this inner for loop, right here, you just shuffle your training set, so that you don't iterate over the examples in the same order at each epoch. So let's just introduce that as well. Yes.
So I noticed you had less than or equal to 1 on there, but It's pretty much, it's gonna, you have 0 either way.
Yeah, it doesn't
One-
matter.
Okay.
It doesn't matter, yes.
The difference I see in sub-gradient descent as compared to this just gradient descent, we are taking a random xi, yi.
No. So that is the difference between gradient descent and stochastic gradient descent, where stochastic gives you the randomness.
Okay, but this is also stochastic.
This is stochastic subgradient descent because the function is not differentiable, so we can't take a gradient steps. So we need the subgradient because that's the only thing we have.
So I am concerned about implementation. So am I going to look at every training example inside the loop of epochs?
Yes. That's the vanilla version. You can decide to sample things. There are so many tweaks that you can make here. So this is the version that you probably will want to implement before you do any tweaking.
Talking about subgradient, can we find subgradient for any non-differentiable function?
Now, it needs to be continuous because that's important.
For example, the L1 norm.
The L1 norm has a subgradient. Yes. The L1 norm looks like a V. The L1 norm basically has an absolute value in it, right? And the absolute value looks like a V, so it's 2 lines. Anywhere except at 0, it's differentiable. At 0, any line is a gradient. In particular, the x-axis is a subgradient. Yeah. We can talk about this offline if you want. Was there another question? Other questions? Yes.
Why don't we just pick the one item instead of each training?
Yeah, so the theory of it is for one item, but going over the entire training set gives a more stable result.
Can you do something like this with kernel SVMs?
It turns out you can't, at least not trivially, and partly because, you know what, hold on to that thought, because I'll be getting to kernels in about 5 minutes. Let me just add a couple of other points. There was a question about the learning rate. Who gives you the gamma t? Many ways of doing this. The theory for stochastic gradient descent tells us that any schedule for learning rates is okay, provided it's square summable but not summable. What that means is every learning rate, every step size should be positive, and the sum of these step sizes from 0 to infinity should the sum of the step sizes should be infinite, but the sum of the squares of the step sizes should not be infinite. And if that confuses you, think of the step size gamma t is 1 over t. Always positive. In fact, if you want to avoid the infinities, let's make it 1 over t plus 1. Always positive. Sum over t is infinite. This series does not converge, but the sum of the squares converges. In the literature, there are many ways of using defining the learning rate. There's a fantastic paper by Leon Bourdieu from mid-2000s, which the title of the paper is Stochastic Gradient Descent Tricks. If you want to implement stochastic gradient descent and make it industrial strength, you have no excuse not to read that paper. It gives you a bunch of kind of collected advice on making stochastic gradient descent work. And one piece of advice that he gives is, use this as the learning rate at the tth time step. If C is the trade-off parameter and gamma naught is, a parameter that you choose by cross-validation, the first learning rate, the first step. Then subsequent steps can be chosen as this function. Turns out this seems to work well in practice.
I feel like I missed something. We're using multiple learning rates?
Yes. Gamma has a subscript.
Why?
Because you want your...
Huh? Did we talk about this?
Maybe not. In fact, I'm talking about it probably now. So in perceptron, for example, we never changed the learning rate. And learning rate was always a bit of a mystery. The stochastic gradient descent, the intuition behind using multiple learning rates and actually a decreasing learning rate is fairly clear. You want to reduce the variance of your classifier as it gets more and more, as it gets closer to the origin or to the minimum. So you want to take smaller step sizes, and that's why you use this. And this shows up a lot in the neural networks, perceptron literature as well.
Why don't we use it in perceptron?
We will, in fact. The right way to do it is, we are getting close to, that's a good point, in fact, we should. It turns out, for the theorem, for the convergence theorem, we don't need it. But for stability, it's probably a good idea to have that.
Since our learning rate is monotonically decreasing, is that why it's okay to just do epochs 1 to t?
Yes, yes. After a point, these things don't matter.
It doesn't
Yeah,
matter.
they're basically not changing your weights anyway, might as well just, yes.
So, I think, so C is, we find C by cross validation. Right?
Yes.
So, do we have a range for C?
In fact, this is mentioned in the homework. Typically what you do is you pick C in orders of magnitude. So I can tell you what I do. In pretty much every experiment that I run, I pick C between, say, from the set of 2 power 0, 2 power minus 1, 2 power minus 2, all the way to 2 power minus 10. And I do cross validation over these 10 or 11 things. You can do 10 powers or whatever. Those of you who may have at some point seen liblinear, the C here is the same as the C parameter in the liblinear command line. So this is a good recipe for the learning rate. It's just one of many good ways of picking learning rate. And with respect to the theory, as the number of iterations, so what we care about with this kind of an algorithm is how quickly can you get to within epsilon of the best objective, the true minimum. And there is a lot of theory. I'm kind of glossing over this just to give you the flavor of these results. For strongly convex functions, just think of it as just convex functions. When you have training examples with n, when you have n training examples and where each example is a d-dimensional vector, vanilla gradient descent, not stochastic, vanilla gradient descent takes roughly n times d steps to get within epsilon. Stochastic gradient descent does not have the dependency on n. Now think about this. I'm claiming that here's a learning algorithm that gives you all these fantastic here's a learning algorithm for a classifier that comes with all these fantastic fact guarantees, and this algorithm does not care how much data you have to get to a certain quality of the classifier. So the number of steps needed does not depend on the size of the training set. So this is one of the reasons why stochastic or stochastic gradient descent is considered to be probably the right kind of framework when the size of the data becomes really large. So for example, let's say you have a training, this is maybe towards the end of the semester I'm going to contradict my point right now, but we live in the land of big data. So this training sets may get larger, and so we need algorithms that do not strongly depend on the size of the training set. If possible, it will be nice if we can come up with a learning algorithm that does not depend on the training set size at all. And stochastic subgradient descent for SVM has the property. There's this, again, another paper called the trade-offs of large-scale learning. Basically the point being, this is the right algorithm when you want to do large-scale machine learning. So, questions?
I guess it has to be an even distribution of examples.
What's even?
What's what I'm looking for?
Uniform?
Yes.
Why?
Consistent.
Very good, Sam. Very good.
Well, if you pick, if it's only dependent on D, you pick enough examples, and they all happen to be clustered right here.
Right, so you're assuming certain regularities. In fact, you're not assuming that. In fact, what you're assuming is that if you say, let's say this is a space of all examples and of all possible features, of all possible inputs, and your training set only comes from this region. The hope is the test set also comes from this region, because that's the game we are playing across this whole. I mean, that's the game that kind of props up. That's the assumption that props up a lot of machine learning. So yes.
So so it doesn't really depend on the size of your training set, but if that's the case, why do you need a really big training? Why do we often have these really big training sets? Or is a lot of information now basically useless?
Not quite actually. Typically, more data is always better because these dimensionalities are also very big. So you may not have enough statistics to cover the space, so to speak. And this is for SVM. Very often our models may be different, especially when you go to nonlinear models. This becomes a definite concern. This is just getting to within epsilon of the best value of the objective for this function. Things may change when you move to different objective functions. Things may change when you move to more complex classifiers, because we still need a lot of data for generalization. Remember that there was this term involving in order to the sample complexity has to be more than that term involving the VC dimension, right? So that still holds. Only if you have those many examples can we make any claims about the quality of the predictor in the future. So generalization still needs a lot of data. This is given a particular data set, getting to the bottom of an objective function for that data set. So there are three kinds of errors. There is the modeling error, which is your data might come from a certain function, and you are assuming that your classifier is a different function space. Already you may have lost some accuracy, but because the true function does not even lie in your hypothesis space. That's the modeling error. The second kind of error is in this assumption about the loss function. Maybe the loss function does not truly capture the error that you care about. The third one is an optimization error. This only talks about optimization.
What's the Strong convex?
Okay, that's for an after-class discussion. For now, pretend that it's just convex. Yes?
You said optimization error, and that's different than your true error.
Optimization, okay. So error is an ambiguous term here. When I say error, what I mean is how close will your objective function be to the true minimum of the objective? How close will your weight vector be to the true minimum of the objective? So if you're, just as a toy example, suppose I draw these sort of level curves, and we want to get to the absolute minimum. Maybe your optimization takes you along some path and you stop somewhere here. It's not you've lost this much because you stopped early, right? It's a numerical thing. It's got nothing to do with learnability or such things. Okay, so just to remind you, this is the algorithm for stochastic subgradient, and what is surprising to me is, I'm sure many of you have already seen it, but nobody pointed out explicitly that this basically looks a lot like the perceptron. Just compare this. In perceptron, you check for YW transpose X is less than 0. Here you check for less than 1. If the condition holds, then you say W is W plus some learning rate times Yx. Here you say W is W plus some constant times Yx plus this shrinkage term. The shrinking gives you the margin maximization, right? So there are two differences. There's the shrinking and this condition about when to update. But even if the condition is not satisfied, if the condition is not satisfied, perceptron makes no updates. If the condition is not satisfied, SVM still shrinks the weight vector so that you can get, the margin can be made a little wider. So that's a kind of an interesting comparison. At least I find this to be very satisfying, a nice unification, because perceptron was invented just, here's an algorithm. Whereas SVM comes from all this, has this formal theoretical backing, and it arrives at something extremely similar. And so that's kind of good, which makes us wonder, or at least makes a lot of people wonder, is the perceptron algorithm, this update, if I run it in the batch mode over multiple epochs, is that also minimizing, is that also doing some sort of stochastic gradient or gradient descent? Because it looks so similar, right? It turns out it is. There's something called the perceptron loss. So remember the hinge loss. The hinge loss for a weight vector given an example is max of 0, 1 minus yw transpose x. The perceptron loss gets rid of this 1 and makes it a 0. So it is max of 0 and minus yw transpose x. So if you write down the empirical risk minimization without the regularizer and define loss to be this quantity and write down, derive the stochastic subgradient descent for this particular loss, you will get the perceptron algorithm. I strongly encourage you to actually convince yourself that I'm not lying to you. So write down the loss function with this perceptron loss, take the subgradient, and it will also give you an exercise in deriving the subgradient. And you already know what the answer looks like, because the answer is the perceptron algorithm. So try to get it. So from the optimization angle, SVM minimizes the regularized hinge loss, and we looked at an algorithm that uses stochastic subgradient descent. It's super fast. It drives a lot of industrial strength machine learning. It looks a lot like perceptron. The perceptron does not maximize the margin width. But remember that there was a homework question in one of your, maybe homework 2 or 1 maybe, where you implemented the perceptron and you tried out something called the margin perceptron, where you fixed the margin. That's kind of going at the same sort of intuition. You're asking for the margin to be this much. And this is very similar to the margin perceptron, in fact. In fact, the margin perceptron could be, instead of 0, it's some margin, and there's no regularizer. That's basically a margin perceptron algorithm. Try it out. There is still, this is all nice in theory, but in practice, when you actually, or at least I find it hard to learn about these things unless I actually implement it and see how it works. So, in particular with these kind of things, convergence becomes a bit of a tricky thing. So, and that's why I think it's a good thing that you guys are doing this homework, because you could try to print the objective value after every epoch to see how fast or slow it converges. This is not the only algorithm for SVM. In fact, the popular linear package does not use stochastic subgradient descent. It uses another algorithm called dual coordinate descent, and there are other learning algorithms for support vector machines also. Questions? Yes?
You just mentioned that convex optimization theory does not care about the learning rate. So if we choose a very large learning rate, that every time, everything is missed the optimization.
It still cares about the learning rate, because the learning rate should be positive and summable and, square summable and not summable.
If we choose a constant number,
if you choose a constant less than 1.
a constant less than 1.
Yes. But yeah, that will.
It will guarantee that you.
In expectation. What that means is, if you run this to if you run this to infinity, I mean very loosely, if you run this to infinity, the probability that you will be at the minimum is very approaches 1. Other questions?
We maybe sort of talked about this, I'm going to just need to go through the notes again, but going back to agnostic learning, so what is our hypothesis space here, and is this going to give us the hypothesis that minimizes the training error so that we get the fact guarantee?
So, no, the hypothesis space here is still the set of linear classifiers.
Okay.
We are still, in the world of linear classifiers, we're still learning the weight vector. The pack guarantee comes because even among linear classifiers, there is a hierarchy. Some linear classifiers have lower VC dimension than others for a particular data set.
But in order to have the guarantee from agnostic learning, we have to produce an algorithm that gives the minimum training error, right?
No, we need to produce an algorithm. No, the pack guarantee looks like the generalization error is greater than training error plus VC term. It makes sense to give the minimum training error because you want to reduce that generalization error as well. But if you don't care, sure.
I see.
But there's a good motivation to get as low training error as possible. And already we've made an assumption. We are not minimizing training error, we are minimizing hinge loss, which is just a surrogate for the training error. Okay, so I have 23 minutes left, and I'm going to change the topics a bit and talk about some kernels and duals and such things. So let's.
I don't think I heard why do they call it support vector?
Excellent question. You're getting there in 2 minutes.
Oh.
Yes. So that's either you've seen the slides or.
I'm not sure why I should support them yet.
Yes, exactly. You need to support the vectors. Come on. So to see why they are called support vectors and what's the story behind this, let's just before going on, let's think about where we are. We've seen the mechanics of support vector machines, the way it's derived, how it's optimized and such things. So really, it's simply minimizing regularized hinge loss. And support vector machine is a much nicer name than the regularized hinge loss machine or something like that. But that's not the real reason why it's called support vector machine. What we have is just a class of algorithms that can learn linear classifiers by tweaking with this loss and regularizing. And in this case, it's hinge loss that we are optimizing. But the problem is, we are still in the world of linear classifiers. What if we care about training a classifier that's not linear? What if the separating surface was not a hyperplane, but say a hypersphere? Every point inside the sphere is positive, every point outside the sphere is negative, or something like that, an ellipse, for example. One answer is something that you guys have already tried in your previous homework. Say you want to generate, let's say this is a true classifier, and I think I've set this up so that no line separates the positives and the negatives. How do you solve it?
Map it into linear space.
Map it into a nonlinear space, actually. This was question 1 from your previous homework, roughly. So what you do is you transform all the input points into a different space that might be nonlinear. So the original space was this pair, x1 and x2, the 2-dimensional space. And if you transform it to this 4-dimensional space of x1, x2, x1 square and x2 square, and I try to write down a linear classifier in this space, this concept becomes separable. Before we move ahead, questions about this, because this is a crucial point.
you have the cross term there.
I just didn't want to, because I knew it was a parabola. But yes, you could have cross terms, but you could do other things.
So in this case, you can see what the shape of the space is in practice. How
In practice, you have no idea. In practice, you just hope, you try things and you hope it works. And in fact, you cross-validate over different feature sets. But this is one answer. And that's good, and this, it seems like we've already solved the problem. But there's another issue here which we'll try to get to in a minute. But just to remind you, we're still in the world of SVMs, and we saw that this was an objective function that we cared about minimizing. This was before moving the max into the top, and we still had this slack variables and all that stuff. So this form of the objective, or including even the one with the transformation with the max, is called the primal objective for the support vector machine. And this name primal suggests that there must be a dual. So there's another objective called the dual. We're not going to talk about optimization theory here because that's an entire semester of class. In fact, you know what? I've heard there's a good optimization class in the math department that's offered in this fall. I don't think you can really claim to understand modern machine learning if you do not understand optimization. So those of you who are around next fall, see if you can join that class. So for any optimization problem, you can write down for any optimization problem that's called the primal, there's a formal constructive way of defining another optimization problem called the dual. And it turns out that this dual has the property where if you maximize the dual or minimize the primal, they will end up at the same objective value. So if you care about minimizing the primal, and if you instead maximize the dual, and if that dual is an easier problem, you may have gotten a computational gain. If this seems confusing, it's okay, it doesn't matter, I'm not going to stress this point. It's one of the more, at least personally, it's one of the more interesting parts of optimization, but it doesn't matter. It also lets you analyze optimization problems, and in particular for support vector machines, the theory of optimization, I'm just going to state this without proof. The theory of optimization tells us, let's say that given a training set, xi, yi, you write down the objective, let's say you run the optimization to absolute convergence, not to within epsilon, but to actual convergence. Let W be the minimum of that function, of the SVM objective. Then it can be shown that suppose you introduce these new variables called alpha, one for every training example, alpha 1 through alpha m, then it can be shown that the W is actually simply a linear combination of all the training points of yi xi. So W is simply the sum of alpha I, yi, xi. It's just a linear combination. In fact, alphas are positive, so it's called the conic combination. And this should not be extremely shocking given the nature of the update rule that we just saw. We saw that W is, in the case where you do not, when the margin is violated, it is some shrinkage, so 1 minus gamma times W plus some C yi xi, some C times R, some gamma. It looks like this, right? This was the update rule that we saw. So at each step we are adding some y times x. So it's no shock that the final optimum value is simply the sum of these kinds of terms. You can just unroll that recursion if you want to get to that state. But these alphas actually have some very interesting properties. It turns out it's not just that the final weight vector is the sum of these, is a linear combination of yi xi, but also if you think of all the training examples, remember we've introduced one alpha for every training example. For every case when alpha is 0, the example will be correctly classified. For there's one alpha for each training example. For every example where alpha is 0, that example will be correctly classified and on the better side of the margin, let's say, outside the margin. If alpha is 0, so every point outside the outside the margin will be assigned an alpha of 0 at optimum. Every point that is on the wrong side of the margin, so that's something not like the plus, but something like, actually no, both these plus and the minus, alpha will be equal to that C. Remember the C term that we had in the trade-off term in the objective. For all points on the wrong side of the margin, alpha at convergence will be equal to C. That's not right. And for every point that's on the margin, like the ones that actually define those lines, alpha will be some number between 0 and C. It will converge to some number between 0 and C. This is just, it comes from the theory of optimization. If you care about it, this is a direct outcome of the KKT conditions for optimization, but if you've not seen it, don't worry. So, just to summarize, the final weight vector at optimum will be a linear combination of yi xi, and only those points that are either on the margin or on the wrong side of the margin will have a say in that final weight vector, because these points have an alpha equals 0. So all these points do not contribute to the sum. So the hyperplane is supported by these points that are on the wrong side of the margin or on the margin. So these points are called the support vectors. All training examples where alpha is not 0, they are called support vectors. And that's really the reason for this name, support vector machine. But the name part is just, to make this interesting, but it's the idea here. This is an important property for SVMs, the fact that your final weight vector is a linear combination of yi xi over all the training set. And only those points that are misclassified or are close to being misclassified, namely these points, define the W. Yes?
Now, when you're doing the stochastic gradient descent or even batch gradient descent, you start off at a W that's not at the optimum position.
Right.
So it's going to have updates from those other ones.
Right. So in fact, that's why that's what I wrote down was not the valid proof. The way to prove this is actually to consider the dual and look at basically take the derivative of the Lagrangian, and it holds. It still holds. It just so happens that the SGD kind of an update makes it easier to see it, but that's not the proof.
It's just the optimal solution has these properties.
Yes.
And we're approximating the optimal solution with our stochastic gradient descent, so then we can just go with it.
Yes. In fact, when I mentioned liblinear uses a different algorithm. Liblinear does not even search for the W. It just searches for these alphas, because if you find the alphas, you can find the W. So instead of searching for the W, it searches for the alpha, and that's really what's called the dual problem. These alphas are the optimization variables in the dual problem.
Is C a value between 0 and 1?
No,
or?
C is a positive number. C is the hyperparameter that you give to the that trades off between overfitting and underfitting. It's the constant on the hinge loss. Questions? Other questions? This is an important property just for support vector machines.
So, say I have a friend who wants to do support vector machines by hand. Would it make sense to look at your points and then choose some initial weight vector that's like you can find the two closest points and find the midpoint between them or something, and kind of start there?
Right. So, first of all, if you're going to have your friend do this manually, then you're not a friend. You're probably a teacher or something. Teachers now. But in any case, actually to do that, that kind of visual inspection works for 2 dimensions. As you go into higher dimensions, this becomes effectively equivalent to solving the optimization problem, because you're trying to find those 2 points that are closest, which means you need to search over the space of all points, identify which 2 are closest. So min, you have a min over there, over the distance, which is an optimization problem. So the intuition is correct. Unfortunately, it does not translate to an algorithm that's not an optimization problem. And moreover, initialization really doesn't matter here because it's convex. We're going to get to the bottom of that wall in here. So the initialization is okay, it doesn't matter. You first. LibSVM is a version of SVM that works in the dual. It also searches for the alphas.
Why was it important to randomize our weight vector for perceptron?
It's not. It turns out even for perceptron, if you write down perceptron as a stochastic subgradient descent over the perceptron loss, it's convex, so it's okay.
My question was that we were trying to use LibSVM and LibLib. We give NMB of both and same value of C. We saw that LibSVM was twice as accurate as LibLib.
Yeah, that's because LibSVM, I think, in default uses a different kernel. So actually, that also is an indication that we should move forward to start talking about kernels. So one of the main points here is the final weight vector is simply a linear combination of yi xi, which means let's now do a little bit of algebra. How do we use this final weight vector? When a new example x comes in, you take the dot product of x with w, look at the sign of that, and look, if it's positive, you say positive, else you say negative. But you know that your w is the linear combination of these weights. So let's just substitute that, and just moving the summation out shows that w transpose x is simply a sum over. So in order to computing w transpose x is equivalent to remembering all these alphas and the entire training set, computing the dot product between every training example and x, and taking the weighted combination using the alphas and y's. I've done nothing here. I've just plugged this summation into this w. So effectively, the only computation that's needed to make your final decision, if for now let's pretend that memory is a solved issue. If you remember all the w's, if you remember all the entire training set and the alpha, all you have to do is, given a new example, compute the dot product between that new example and the entire training set and take the weighted average. So really the only thing that's needed is this dot product. Make sense? Questions? So this is a property that just jumps out of the fact that your final weight vector is this linear combination. But this is true even if this vector x is your feature vector. This property holds even if your feature space had been transformed. Say you had to do a feature transformation phi before applying your classification, same property holds. Every place that you see x, you use a phi. So instead of doing x transpose x, you're doing phi transpose phi. Phi of xi transpose phi of x. And an example of a phi, we've already seen such an example, you do this quadratic lifting. So basically the only thing that's needed is this dot product. That's the only computationally complex step that's around here. And of course you need to do this for the entire training set. That's another problem, but we'll deal with one problem at a time. So let's define this dot product in some higher dimensional space. I don't know what space. It could be just the original space or perhaps a transformed one, because the identity is also a feature transformation. So let's define this thing as a function that takes two vectors x and z and produces a dot product in the blown up feature space. So let's call that function k. So effectively, what I have managed to show you is the sign of W transpose phi of x is exactly the same as the sign of sum over the entire training set. Here I sums over the entire training set. Sum over the entire training set, alpha I, yi, k of xix. Questions before we move ahead? Have we done anything that's spectacularly different or new here? We've just done some algebra, moved around, introduced this new term that the only really tricky bit here was to point out, was to observe that your weight vector is just a linear combination. Once you get that, you just get the whole, everything else just is algebra.
What's phi?
Phi is your feature map, like this thing that you had. Phi is this high dimensional feature space that you want to transform your points to. What is z? Z. So I'm just defining this function here. K is a function that takes two vectors, x and z, projects each of them to the high dimensional space, phi of x and phi of z, and takes the dot product. The way we apply k is here. K of a training example, comma, the new point that needs to be classified. Yes? No? Okay. Okay. So I've just done some algebra here. I've defined k to be this dot product in the blown up feature space and pointed out that instead of calculating W transpose phi of x, I could just as well equivalently calculate the sum over the dot product values, but I've done nothing here, right? I mean, if you have to compute, if I have to compute k, to compute k, if I had to explicitly do this dot product, I've gained nothing. This is just a rewrite of something. But here's the key point, maybe I'll stop with this. If suppose I can compute the value of k without ever explicitly computing the value of phi, for a certain function phi, if you give me a function phi, suppose I give you a way of computing the value of this dot product in the higher dimensional space without asking you to ever evaluate that function phi. It's a computational trick. Then you save a lot. Because imagine, suppose your phi, your feature transformation takes you from, say, the n or the d-dimensional space to a new higher dimensional space that has, say, d square elements. So now a new example comes in, you take your example x to this d square dimensional space, you take your training examples to this d square dimensional space, product, completely pointless. You're paying a lot of computational effort. If I tell you that you can compute this function faster than explicitly blowing up, then there is some hope for, say, getting some computational advantage. This computational advantage is called the kernel trick. This dot product in a higher dimensional space is called a kernel function. Dot product in any space is called a kernel function. And the kernel trick is a computational trick that enables us to compute dot products in higher dimensional spaces without explicitly blowing up the feature space. Given that it's exactly end of the lecture and I have at least 10 more slides, I'll stop now. So we'll start our next lecture with the kernel trick. I'll give you examples of how such a trick might exist and point out how this can be used. At this point, in fact, even though I've not shown you how to use the kernel trick, you can solve almost all of the homework. including this kernel question, even though I've not told you what a kernel is, a lot of it should be accessible. So take a stab at it because it talks about the kernel and how it relates to a vector algorithm. And of course I have my office hours and stuff like that.